I will discuss today, it's a bit loud, sounds loud. I don't know. Low a little bit. Yes, I don't want to scream and scare you away from here. So, it's an honor to be a speaker in this Latin American workshop, and it's also a further honor to give the first opening the talk in the workshop. Thank you very much to Danielle and to all the organizers and the Institute for hosting me. I will discuss today piezomagnetism. And it's something that we are not very used to. It's a topic that is, I don't know, I heard about very recently. And so I brought a little bit of a gadget, so you tell me what kind of noise you hear. Do you recognize this noise? It's quite annoying, right? So what is it? This is the noise of a transformer. When you're waiting for the bus in the street or close to your apartment in the city, there is a power transformer nearby, and this is what happens in different tones. Okay, this is caused by a phenomenon of piezomagnetism in part. When you have a transformer and an iron core, the iron core vibrates at the frequency of the AC current in the transformer. And this vibration is transmitted to the case of the transformer and very often amplified to the point that you want to turn that thing down because it's driving you nuts. However, there are also good connotations for piezomagnetism. And this is this speaker here. It works with vibration. It's using the entire blackboard as a speaker. And it does not work at all when I have it in my hand, right? It only works when it's transmitting here. Now something happened with my application, but you heard already working. I don't want to spend more time with this. So these are two examples of how piezomagnetism works. Piezomagnetism essentially is the coupling between, it's a linear coupling between the lattice and the magnetic field. Most materials have a quadratic coupling. And what that means is that small magnetic fields don't have much of an effect, because you need to apply really large magnetic fields to see an effect when the coupling is quadratic. When the coupling is linear, it's much bigger. So let me go ahead and tell you about piezomagnetism in uranium dioxide, and also some electronic nematic state in metal, which is cerium, rhodium, indium-5. So we have my talk split in two, one for an insulator and one for a metal. They have very, very different properties. I work at the National Magnetic Field Laboratory. This is the, my position is at the pulse field facility. We run pulse magnetic fields. And I work at Los Alamos in New Mexico. The sponsors are the National Science Foundation, the state of Florida, and the Department of Energy. This is the outline of my talk. I will discuss first an introduction to the magnetic fields in pulse field laboratories. Piezomagnetism in uranium dioxide is an old dog that shows new tricks because of a specific, very special antiferromagnetic state developing below 30 Kelvin. I will also discuss cerium, rhodium, indium-5, which is a metal, and in principle in zero magnetic fields and zero pressures is isotropic, but when you apply large magnetic fields, it shows anisotropy, an emergent anisotropy height fields. And these two materials show noble phases that are very uncommon in physics, and I think this is the reason why this talk fits in this workshop. This is my list of collaborators, and I don't need to go in detail. You will see some of the work that we did together cited along the talk. But I have collaborators in Los Alamos and also abroad in France and Dresden, Lausanne, etc. I don't have many collaborators from Brazil right now, so this is my chance to convince you that this physics is interesting and I can do some collaborations. Sorry. Okay, the National Magnetic Field Laboratory is split in 3 different centers. two in Florida. The headquarters is in Tallahassee, Florida for DC magnetic fields. The low temperature, high magnetic field laboratory is in University of Florida in Gainesville. The pulse magnetic field laboratory is in Los Alamos. The reason is here is very clear in the next view graph. Tallahassee, this is our 45 Tesla hybrid magnet that consists of both a superconducting magnet and a resistive magnet put together to produce a constant magnetic field of 45 Teslas. If you compare this with a typical commercial superconducting magnet that reaches something like 14 Teslas, this is 3 times the biggest PPMS. This is what we have at Los Alamos, and that's why we sit there. There's a motor generator that used to be, was designed for a nuclear power plant in Tennessee, but this power plant in the 70s was canceled, and the motor generator was sold to Los Alamos for $1 plus shipping. The shipping was kind of expensive though, about $1 million. With this motor generator, we feed our biggest magnets. You produce electricity to power the magnets. And here, this is a facility in Tallahassee, and so in Florida, in Gainesville. And what they do there is that they take the sample into a cryostat, and they cool it down to millikelvin temperatures, like 1 millikelvin, or less than 1 millikelvin, using the magnetization stages. And this is very, very, very low temperatures. And then when they apply a magnetic field of 20 Tesla and divide it by a fraction of a millikelvin, the number turns out to be very high. And that's why it's called the high V/T facility. This is a limit where all physical properties are completely dominated by the magnetic field, not the temperature or other parameters. These are the magnetic field profiles that are produced in the facility. This scale here is time, 2.5 seconds. And this is magnetic field. Everything in blue here is what is produced in the DC facilities, except that, you know, I shrunk the time scale, but you can have it forever. And in Los Alamos, we produce profiles that can keep the magnetic field constant at 50 Tesla, 60 Tesla, or a pulse magnetic field that breaks the 100 Tesla scale here. And this is happening for a few milliseconds. So I know from the abstracts to this workshop that the majority of you are theorists. This is what it looks like. But this is my chance to tell you what we do. We do experiments in milliseconds. So typically, even if you're an experimentalist, you will think that you need 20 minutes to take one data point in the PPMS. How are you going to do any measurement in 10 milliseconds? And this is part of my job today, to show you that that works. This is a 32 Tesla superconducting magnet in Tallahassee. And this is the competition. We're not the only ones. We are here at Los Alamos, o más grande del mundo. You understand that, right? Grande del mundo, exactly. And this is whether. Yes. I hope that my accent is not too bad. But then there's a facility in Dresden that is very, very close, another one in Toulouse, Wuhan, and Tokyo. And it could well be that in January or February, Toulouse beats our record, but we have the record since 2012. They are very, very close. They're in a new capacity bank as we speak for this to beat this record. Why do we use large magnetic fields? Well, the explanation is very clear here. We use large magnetic fields because energy-wise, the magnetic field is producing, giving you an energy scale that you can compare to the temperature scale. And this equation here, very simple, tells you that 1 Tesla is roughly 1 Kelvin. So when you're going to work with energy scales and you're going to try to control your physics with a magnetic field and fight against temperature disorder, the magnetic field is important. So you need to go to low temperatures and apply magnetic fields, and the magnetic field dominates the temperature scale. But there are also interactions that are magnetic, sometimes electric, and the magnitude of the interaction is what limits what the physics that you can do in the experiment. So the larger the magnetic field, the larger the family of compounds that you can study. So these are the number of experiments that we can do in magnetic fields. So electric experiments, a long list here, magnetic property experiments, thermal properties, optical properties, lattice. This is just a list of different experiments that we can do. We can do almost every single experiment that you can do in a DC lab, except for X-rays or some NMR that requires extremely high homogeneity in pulse magnetic fields. But everything else is possible. Even specific heat measurements that take a long time in the PPMS, we can do it if we make the sample sufficiently small. So this is an example of stuff that you can study with large magnetic fields. This is temperature magnetic fields to 60 Tesla. And these are a collection of quantum magnets that we discussed in a review article from 2014 in the Review of Modern Physics, where these quantum magnets are materials that are non-magnetic in zero magnetic field, but you can induce magnetism by applying field and closing the spin gap, and then when you close the spin gap, the system orders. And then you can study them, all of these phase diagrams, with the focus typically in these phase transitions. These are transitions of the second order that when they are happening at zero temperature, they involve a quantum critical point. So all of these transitions are quite interesting from the point of view of possible frustration in the spin lattice and the dimensionality in relation or in connection to a quantum critical point. So you can study the effect of these characteristics on the universal behavior of these materials at zero temperature, which is quite interesting. So this is a lot of introduction, but I hope that you're patient. This is another example of stuff that you can do at very high magnetic fields. These are quantum oscillations in high TC superconductors. Up until not too long ago, I'm gonna say no more than 10 years, or roughly 10 years, the very existence of a Fermi surface in high TC superconductors was doubted. People did not know for sure, because quantum oscillations or any other property related to the Fermi surface wasn't yet measured. Well, high magnetic fields were critical to determine the first Fermi surface observations of high TC superconductors, and this happened in research that was done in Toulouse, in Grenoble, and in Los Alamos, in Dresden. Now it's something that is common, and it shows up in almost every high magnetic field laboratory. These oscillations in the physical properties, essentially, carry information about electronic orbits in the Fermi surface. So you can see here an example of 530 Teslas oscillation. And this is an oscillation that actually happens as a function of the inverse of the magnetic field, but here for display purposes are plotted this way so you can see how high magnetic fields you need to see it. And then you can resolve these small pockets of the Fermi surface with the quantum oscillations. And this is for the yttrium baryon copper family, and this is for the mercury baryon copper family. You see 800 Tesla is a larger frequency. So what is the point here? The point is very simple. You have an electron that is moving in a magnetic field, and because of the magnetic field, it turns in an orbit. However, the material has impurities. If the electron suffers scattering, and on the way, in the trajectory closing the orbit, then you don't see the quantum oscillations. They get scrambler and scatter around, you don't see anything. In order to have an orbit that is smaller than the distance between impurities, you need to apply a very large magnetic field. The orbits get smaller and smaller and smaller. Now, these orbits don't take any random value. They are quantized. They are quantized, and when each one of these so-called Landau levels crosses the Fermi surface, you get a peak in the property that you are measuring. It could be the magnetization or the magnetoresistance. And then this allows to calculate the area of the Fermi surface. And this is critical. You cannot do it without high magnetic fields. So I am interested in the lattice. And the lattice can be studied with something called the coefficient of thermal expansion. It's a derivative of the loop volume with respect of the temperature. This can be written as the derivative of the average interatomic distance respect of the temperature. And this, in turn, can be calculated as the mean vibrational energy per atom. That tells you what is the distance between atoms, and the derivative gives you the lattice thermal expansion, which in turn can be written as the specific heat. So this is to show you that the lattice contains information that is well accepted in the community as a thermodynamic property of a material. You measure the lattice, you measure the thermodynamics. Not only that, The coefficient of thermal expansion is unobservable. The specific heat is unobservable, and these quantities can be calculated. And then you can do direct comparisons between the theory and the experiment. And this is fantastic. It does not always happen in condensed matter physics. There are many materials where, many body problems of free electrons and stuff are very difficult to calculate. Beyond that, the lattice is what you see. And it's very close related to the thermodynamic properties of materials. And this is the main motivation for me to study the lattice of materials in high magnetic fields. I use a light source that is sent through a scrambler into a fiber. This fiber has gratings in the core. The sample is attached to the fiber. So when you apply a magnetic field and the sample expands, the fiber is stretched. And the pitch in the grating is stretched too. So you can see that I send white light, represented by this multicolor photon here. I receive back a color light of one color, send it to a spectrometer, a fast camera, and then I get the reflection spectrum. And this reflection spectrum shifts when the sample changes dimension. The advantage of this technique is that there is no electromagnetic interference. So when you have the demand sample in a noisy electromagnetic environment, the data comes out untouched, essentially. This delta L over L on the sample is directly proportional to delta lambda Bragg divided by lambda Bragg. These fibers work at 1550 nanometer frequencies, and the ultimate experiment looks like this. You have a sample that has a fiber attached to it. The trick of the experiment is that the fiber needs to follow the sample. So you need a very good gluing technique for that to work. Ultimate resolution with this technique, 10 to the minus 8. So 1 part in 100 million. Not many experiments have that type of resolution with this simplicity. That, for instance, you measure transport, how easy it is to measure 1 microohm. So a sample that has a transition between 0 and 1 microohm. This is 1 part in a million. That will be very, very difficult. You have to struggle to measure a superconducting transition that has a height of 1 microohm. You have to be the best thing in the world to do that. And with this technique, you could do it very easily because the resolution is 100 times better than that. So let's go inside. The properties of uranium dioxide come back to the Manhattan Project in Los Alamos, when the lab was secret. At that point, uranium dioxide was synthesized for the first time. It has a cubic unit cell. This is face center cubic with the uranium atoms on the sides, and an oxygen cube inside the uranium cube. This material is paramagnetic down to 30 Kelvin. Below 30 Kelvin, it shows an anomaly. However, this anomaly, which was measured in Los Alamos in the 40s, was kept secret for a number of years because of the Manhattan Project. There were people working with uranium for other purposes, and this was not allowed to publish. However, in '52, the curves were finally published, and the authors of this paper mentioned that this anomaly at low temperatures is probably related to a phenomenon of anti-ferromagnetism, a theory of which was recently given by Van Vleck in '41. So this was very, very new at the time this was first mentioned. What happens is that you cool down, and the atoms at the moment on uranium form an organized antiferromagnet that is kind of peculiar, because being cubic, if there's no preferential direction in the lattice, the only preferential direction is the body diagonal of the cube. So the magnetic moments point along the body diagonal. Measurements of thermal expansion show that this is a first order phase transition. Here is delta L over L, and here is the coefficient of thermal expansion. Not too different from the specific heat. Recent work by Santini, Carretta, Caciufa, mostly in Italy, I think, have proposed that a large coupling between the uranium dipole and electric quadrupoles in the unit cell are responsible for the first order nature of this antiferromagnetic transition. What is uranium dioxide? Well, uranium dioxide is the prime nuclear fuel, and it's perhaps the most published actinide component in the world. If you go for Google, you will get that there are 600 papers that mention uranium dioxide every year. And this is in Web of Science. 20% of all human-made energy comes from uranium dioxide. However, it has a problem. The thermal conductivity is one of the lowest thermal conductivities known to technological materials, and we don't know why. This is the inverse of the thermal conductivity, so the thermal resistance. So the thermal resistance has a peak at the antiferromagnetic transition, and even at room temperature is several times worse than thorium dioxide that has the same lattice parameter and the same symmetry. So why is that uranium dioxide has such a poor thermal conductivity? This is bad because in a nuclear rod, in a nuclear fuel rod, hotspots kill and destroy the fuel bar. These hotspots are formed because the heat is not easy. It doesn't easily transmit outside of the fuel cell. So another mystery is that when you apply a magnetic field, the thermal conductivity changes. So there are many hints here that say that the magnetic moments, the magnetism in uranium dioxide, is connected to the material's ability to transport the heat. And this is an important technological problem too. So a number of authors, including Amoretti and Caciuffo, again in Italy, have proposed from neutron scattering experiments that there is a mode of the oxygen atoms. It's a Young-Teller distortion, a dynamic Young-Teller distortion that is a candidate to scatter phonons and reduce the mean free path. We are out there to try to understand what is the connection between the lattice and the magnetism. So this is what I did. I measured the lattice strain as a function of the temperature. I found the first order phase transition, and then at each of one of these points that is marked here in this strain versus temperature point, I pulsed the magnetic field to obtain the magnetostriction. This is what I got. I'm not gonna speed up right now because I have another half a talk to give on the other compound. But in the paramagnetic state, we see quadratic temperature, magnetic field dependence of the lattice parameter, and this is what you will expect. We did these measurements all the way to 92.5 Teslas. And this is the first surprise. We have a transition that happens at 30 Kelvin. I already told you that 1 Tesla is 1 Kelvin, but then you apply 90 Teslas and you cannot saturate this material at all. So you can see that there are, there's an energy scale that is larger than 30 Kelvin. There is something there in the interaction between the uranium atoms that makes it continue to be quadratic all the way to 90 Teslas. Then the second surprise is that you cool down below the 30 Kelvin transition, and this first order transition is obvious here, and then something else happened. Now, in addition to the quadratic term, a linear term becomes obvious in the magnetostriction. Also, some irreversible behavior at low fields. You take the linear term out of this fit, and you plot it, and the linear term grows from literally 0 above the antiferromagnetic state to something finite inside the magnetic state. And this looks very much like an order parameter. The linear term has a lot to do with what this ground state is in the material. The linear term that appears here at low temperatures is what I mentioned before, is the piezomagnetism. Most materials don't care about the sign of the magnetic field that you apply. You put the sample in your PPMS and your measurement, you measure, and sometimes the magnetic field is up, sometimes it's down. The actual definition of plus and minus is actually relative because it doesn't matter. But for this guy, it does. Because now you can imagine that when you have negative magnetic field, the sample will shrink instead of expand. Does it happen? Well, this is what we came out to prove. Piezomagnetism is very closely related to the symmetry of the ground state. And let me show you here an argument. You have here the lattice deformation proportional to the magnetoelastic tensor multiplied by a magnetic field. The magnetic field breaks time reversal symmetry. We know that for sure. The deformation does not, because it's something static. So the only way to see a linear term in the magnetostriction is to have a magnetoelastic tensor that breaks time reversal symmetry. So minus times minus gives you a positive. So from there you can tell that only certain magnetic structures will produce a linear magnetostriction. This was identified a long time ago by Landau and Shalosinski in 1957, who said the magnetic symmetry of some antiferromagnetic crystals permit the existence of piezomagnetic effect. By the way, all ferromagnetic crystals do that because they absolutely break time reversal symmetry, but not all the antiferromagnetic states. As a matter of fact, there are 122 space groups that describe magnetic order, and only a subset of 66 can allow piezomagnetism. So the thing is that now we realize we can actually tell what the symmetry of the magnetic order is from a bulk measurement like magnetostriction. So this is, again, part of my colloquium I gave recently, so I apologize for the simplicity, but maybe this will be useful for some of the younger members in this audience. The time reversal symmetry test can be done graphically here, following thinking by Tinkham. So if you take an antiferromagnet and you apply the time reversal operator to this compound, and then lattice symmetry element of the material, and if you recover the same lattice, then it says that the time reversal symmetry is not broken. And in this case, linear magnetostriction, actually, they have a mistake there. It's not linear magnetoresistance. Linear magnetostriction is not allowed. On the other hand, if the lattice distortion involved, and you apply the operator for time reversal symmetry, and then use a symmetry element, then this does not work anymore. So in these cases, the linear magnetostriction is allowed. And we believe that this is what is happening here in the uranium dioxide with the non-collinear antiferromagnetic state. So here comes the interesting low temperature part and low magnetic fields. It turns out that this hysteretic behavior at low temperatures is related to something, well, we found this and we think it's related to magnetic domains. Antiferromagnetics can actually have magnetic domains. And this is the demonstration. You do a zero-field cool experiment, the blue curve shows irreversibility, but then you apply a magnetic field in the opposite direction, which is the orange line here, and you see the sample contracts until you reach a crossover, and then at this point, the antiferromagnetic state flips completely to a related state, and then you get this equilibrium curve, change the magnetic field direction again, and the sample contracts instead of expands until you reach the point at which you flip the magnetic domains, and then you reach this other equilibrium state here on the other side. In other words, once you've trained the sample, you can get to the point where a positive magnetic field causes expansion of the sample, a negative magnetic field causes the contraction of the sample, and depending on which one of the two branches you are. And these two branches are two magnetic states that are connected by time reversal. It's very important that you apply the magnetic field along the body diagonal, which is the symmetry, the trigonal symmetry axis in the material. The same thing happens when we use transverse magnetostriction instead of axial. And what happens is that in the paramagnetic state, application of a magnetic field causes a distortion of this type in the cubic unit cell. In the antiferromagnetic state, and on the other hand, it distorts in this way. When you apply a magnetic field and measure the magnetization, you have magnetization versus field. Essentially, nothing happens at first sight, which is consistent, again, with antiferromagnetic domains. If each domain has zero magnetic moment, it doesn't matter when you flip them, because it still has almost zero magnetic moment. However, when you subtract a linear component, you can see that there is a little bit of a loop at 18 Tesla, the same magnetic field at which this magnetic domain flips. So we put together a model to solve this. This was done with André Saúl and Guillaume Radke at University of Paris. And the model is essentially a minimalistic classic Hamiltonian with where the degrees of freedom are the orientation of the magnetic moments at the 4 uranium atoms in the unit cell. So then we take into account the Simon effect, magnetic anisotropy, Heisenberg, elastic energy, magnetoelastic energy. With one interesting caveat, is that the electric quadrupolar term that I mentioned in the beginning was proposed as crucial to cause to be behind the first order phase transition is not necessary. We calculate this model, we calculate, we use this magnetoelastic tensor in this notation, the box notation, and then when we do that, we obtain, let me not distract you too much with the animation here, these figures here. The most important here is that you have the energy difference between two different versions of order. This is this order in the unit cell versus this order. What is the difference between these two? Time reversal symmetry. You see here, in this case, the arrow is pointing out of the tetragon, and these three uraniums here have a circulation in the tetragon. The net magnetic moment of this unit is 0. The net magnetic moment of this unit is 0, but the symmetry, I will say the direction in respect of time reversal is different. This points out and this points inside. Now you can see here that the pink structure shows a lower energy for negative magnetic fields. The green structure shows a lower energy in positive magnetic fields. So we have an asymmetric situation in which if the sample consists mostly of these domains, then the sample, as the magnetic field is varied, will follow this curve. If the sample is made out of mostly these domains, then the energy follows this direction. This curve, the green curve. The magnetization shows very, very, very little structure. However, the lattice shows a huge difference between the green and the pink. We cannot reproduce, however, the transition between one and the other. We don't know yet what triggers this flip of domains at 18 Teslas. There's a speculation that maybe as the sample is distorted, the electric quadrupole component contribution becomes bigger and eventually dominates the antiferromagnetic, the dipole component in the order parameter, and maybe at that point the electric quadrupolar term needs to be included. However, we haven't done it yet. This is something for the future. So now I can show you the animation. As you apply a magnetic field, what you see is this curve here showing the magnetostriction and the moments gradually tilting until they suddenly flip the switch field. This is a very, very nice example of a model that, even though it's complicated, it can still be solved, in part because there are no free electrons, so you can do these computations. If you magnetize partially the material, the domains don't flip completely. So let's say that you start here in zero field cooling, and you only increase the magnetic field up to 8 Teslas. And then you reduce the magnetic field, and you form this little loop here. And then the sample remembers how many of the domains were already flipped in a certain direction. And then the next time you ramp the magnetic field to 8.5 Teslas, you get this one, and then 9 Teslas, and then 10 Teslas, and etc. So this proves again that what happens after the zero field cool is just a gradual rotation of antiferromagnetic domains. This is a beautiful example of studying antiferromagnetic domains, which is usually not possible because the net magnetization is 0. So with this I finish the uranium dioxide, and I will switch to a completely different system. This is now metallic, and I am at half an hour, so I think it should be fine, right? Yeah, 26 minutes over there. Okay, but anybody has any questions on uranium dioxide? Yes. The magnetoelastic energy over here. Right. This is the stagger moment. So the magnetoelastic essentially is a term that contains the net magnetic moment that you observe in each one of the two domains. Correct. Mm-hmm. Yeah, because this is the magnetoelastic tensor over here. Yep. Okay. I'm 100%. It took me 2 years to understand the system. I'm sure that it's difficult to understand in half an hour. But any question, even if it's stupid, in your point of view, I'm sure it's going to be pretty bright for me, because it's a problem that we've been looking at and focused on it for many times. I'm sure we missed stuff. Okay, the next one is metallic. So you're gonna not see many computations and calculations in this one. You have electrons, forget it. Now we start talking about, possibilities, not real ground states. So, emergent phenomena in correlated electron systems in my group is studied in the context of quantum phase transitions that happen when you take a material that orders in zero magnetic field. This is the temperature through possibly a second order phase transition that is suppressed using an order parameter. And this order parameter can be the composition, the pressure, the magnetic field, or the strain. When you suppress this transition to zero temperature, the temperature is not important anymore, and now quantum fluctuations dominate the physics. And then emergent phenomena is observed when, let's say, a secondary order parameter finds the right conditions to develop in the material. And this secondary order parameter can be, for instance, superconductivity. And this happens in cerium, rhodium, indium 5. Fluctuations and time scales diverge at the quantum critical point. Physics becomes independent of the details of the system under study, and then universal critical exponents rule the properties. So this is an excellent test ground for the study of properties, both from an experimental as a theoretical point of view. There are great reviews on this topic by Subir Sakhdev and Jimmy Alcy in the literature. Cerium, rhodium, indium 5 is a compound that orders antiferromagnetically at 3.86 Kelvin. This is the coefficient of thermal expansion again, very much like the specific heat. When you apply a magnetic pressure, this is a pressure example, when you apply pressure in this compound, we're talking here cerium, rhodium, indium 5, and cerium, indium 3, the precursor of cerium, rhodium, indium 5. That is more cubic, this is more 3D, this is more anisotropic, a little bit more, not much, with the rhodium layer in between the indium and cerium layers. You can see, let me see, just focus on the red one that is more simple. The antiferromagnetic state is suppressed with pressure, and about 25 or something kilobars, a new state is observed, that is superconductivity. You make a sample that is slightly different, cerium, rhodium, indium 5, and now the antiferromagnetic transition is suppressed, and the superconductivity is enhanced to the point that these two are now comparable, and they even have a region in which we believe that there is some texturing or superposition of the antiferromagnetic order parameter and the superconducting order parameter, which is very exotic because magnetism and superconductivity repel each other in most materials. So we can do the same thing with magnetic fields. We can use an external parameter such as the pressure and study what is happening here. This is a magnetic field example. Now we have again antiferromagnetic state in zero magnetic field. When you apply a magnetic field, the antiferromagnetic state is suppressed. These are two different directions. Magnetic field applied along the A axis and the C axis. Tn goes down. Then something happens here at 30 Teslas, well within the antiferromagnetic state. There's several things that are interesting here. One of them is that the critical field, it's just proving me absolutely wrong, right? I say that 1 Tesla is 1 Kelvin. Well, that applies only in the simple systems. When you get into a more complicated system, this, like uranium dioxide or cerium, rhodium, indium 5, it doesn't work anymore. You need actually 50 Teslas to suppress this 3 Kelvin transition in cerium, rhodium, indium 5. In addition to that, we observe this. Now here we have two different experiments. One of them is the magnetic susceptibility, which is some noise here, and the specific heat. This is the specific heat that shows an anomaly here. You can see the main transition happens here. This is an expansion of the specific heat in a different scale, Cp over T. I think this is C. Thing is that this noise here is actually quantum oscillations. And the quantum oscillations over there change drastically at these transitions. We believe that there is a reconstruction of the Fermi surface there. But we don't know exactly what is the competing state. We have an antiferromagnetic state with a small Fermi surface here, and an antiferromagnetic state with a large Fermi surface here. And this is paramagnetic. This is kind of curious. Pressure and magnetic fields bring in new stuff. So this talks about the universality of this behavior. You use an external parameter to perturb the order in the state, and then something else. It's like a competition of ground states that we don't see if we don't apply an external parameter. Philip Moll and collaborators did some cute experiments recently on this material. They took a sample, that's just a nice single crystal, and cut little bars using a technique called focus ion beam. These bars, as you can see here, and the energy scale is about 20 microns here, maybe 50 microns over here, and they now can measure the electrical properties along different crystallographic axes. The Z-axis comes out of the plane, and you can see here this is the 1,0 axis in the AB plane of this tetragonal material. This is the 1,-1,0 axis in the plane. And I fell here to show you the background behind this. Why did they decide to do this measurement at all? Well, after doing several of these measurements, they noticed that there was some sort of like a variability of the results between different samples that led them to wonder if there is some emergent anisotropy at high magnetic fields. But they didn't show any of that demonstration. But just take my word for it, they saw hints when measuring large crystals that trigger the need to measure specifically different directions in the lattice. And then in this sample over here, what you have is, again, the same thing, 1,0,0 here in this, and 0,1,0 over here. Two principal axes, two diagonals. And what they see is astonishing. This is the electrical resistance as a function of field. When you reach 30 teslas, some anisotropy appears. One direction, which is represented by the blue arrow here in the plane, shows an increase in the resistance. Another direction shows a decrease of the resistance. And that happens when you apply a magnetic field not exactly along the Z-axis, but slightly tilted along one of the principal axes. So here you can see the magnetic field applied 20 degrees into the red curve, and then the red curve goes down. And then you can see here the magnetic field applies 20 degrees into the blue curve, and then the blue curve drops. And the same thing happens for all of these 4 directions in the AB plane. So this is amazing. This is something that was not expected by any means. Yes? Yes. If the ground state is isotropic, right, you will not expect this transition here. Yes, you see, do you see an anisotropy here, yeah? You see the red curve here, and the blue are slightly different. But the transition is what is new, right? And this was not expected. What they speculate is the electronic wave function is not spherical anymore. Somehow, at 30 teslas, there is something that happens, and the electronic wave function becomes elongated. And when you apply the magnetic field in this direction, you distort it in this way, and then the overlap is different, and then the resistivity drops. And the same thing happens here. But this is, again, a speculation. To the best of my knowledge, there's no calculation on that. This is my job. I will tell you about that in 2 minutes. Yes. So this is what they did. There is what appears to be a broken tetragonal symmetry that is triggered by a magnetic field of 30 teslas when the Fermi surface reconstructs at that field. But then is when Philip Moll and Philip Browning asked me if I could take a look and see if the lattice is having a huge distortion there. Right. And then I tried, and it didn't work. And then I tried again, and it didn't work. It's not so easy to have your sample at an angle with the magnetic field because of the torque. So the sample wants to come back to, to being aligned with the magnetic field. But eventually we did it. Okay, you asked my question before I was completely ready. Another thing that I wanted to show is that the resistivity versus field shows this behavior with a drop here close to the suppression of the antiferromagnetic state. And then when you take the resistivity as a function of temperature, you get these dots here. You can see that the temperature dependence of the resistivity at 49.7 Tesla, which is the suppression of the antiferromagnetic state, shows what is called a non-Fermi liquid behavior. The resistance is linear all the way to sub-Kelvin temperatures. So this is the proof that indeed there is a quantum critical point here. So now we put together the pressure and the magnetic field effects on this phase diagram, and then you can see that they look similar. The antiferromagnetic state is suppressed, right? So then there is a transition of first order here induced by pressure, and there's another transition here that looks very sharp and is induced by magnetic field. So we have, in one case, superconductivity, here we have nematicity. So pressure and magnetic field, surprisingly, are equivalent, have equivalent effect on this material. And I will tell you why it is surprising in a minute. Let me continue with this. One of them is a D-wave superconductor. The other one is a nematic state. So what we have here is a material that is initially partially hybridized because it's not completely local. The magnetic moments in the cerium state, in the cerium positions, not fully developed because of some hybridization between the F electrons and the conduction electrons. How do we know that? Well, it is an antiferromagnet with a heavy mass. Normally, antiferromagnets have a light mass because the electrons don't hybridize with the moments. But in this case, the specific heat shows a heavy mass. The magnetic field induces localization, destroys the hybridization, and you get nematic state. Pressure makes it more hybridized, and then the antiferromagnetic state disappears, and in a D-wave superconductivity is induced. Part of the theoretical challenge here is to combine this information into a universal phase diagram for this compound. But anyway, what is happening there with the lattice? Well, I did the measurement. This is delta L over L versus magnetic field. As you can see, it's quadratic. There's nothing here pointing to any linear magnetic restriction or anything. This is exactly what you will expect for some antiferromagnetic state that, in my definition, does not break time reversal symmetry. However, if you subtract a quadratic term here, you get this. And then when the magnetic field is pulsed up, there's a lot of noise because of the vibration in the magnet, but on the way down, we see an anomaly at 30 Teslas. This anomaly is only 2 times 10 to the minus 6. So if there is something in the lattice, it's extremely small. Something like this has been seen in other compounds, like the strontium ruthenate, the 327 compound, but the magnitude in that material is 100, 10 to the minus 6. This is 100 times smaller than what you see in a typical spin density wave state, like in the strontium ruthenate compound. We repeated these experiments then. Once we observed this, of course, many people ask, well, what if this is just an anomalous, weird noise? Can you repeat this in a DC magnet? We went to Tallahassee and repeated exactly same experiment now in a DC magnet. And in DC magnet, we see the anomaly both ways, sweeping the magnetic field up and sweeping the magnetic field down. Additionally, we see some noise here, but this is not really noise. These are quantum oscillations in the lattice parameter. So this essentially puts the ordering in the XY category. We expect that it's not an Ising type ordering that is triggered at 30 Tesla, because an Ising type order will have a much bigger effect in the lattice. If we didn't have this 10 to the minus 6 resolution, we would have never seen it. And this nematic electronic state and the discussion of the quantum oscillations is now available in a preprint in the ConMat server. This is Priscilla Rosa. That's my Brazilian collaboration, but she actually works in Los Alamos. She is not here. And then you can see here some of the characteristics here. Let me see. The magnetic field is applied at 17 degrees of the z-axis. We have up and down. Here, this anomaly is this metamagnetic transition that helps us to confirm what the magnetic field angle is, because this metamagnetic transition depends strongly on the direction of the magnetic field. So we use the metamagnetic transition, which is not seen here. There is something there, but the noise here is bigger. is very clear over here. And we see this, and we see the quantum oscillations too. So this essentially was a response to the referee in the Nature paper. The referee say, well, what if, now I know that you're the referee. What if the lattice is distorting there, and all this anisotropy is just a lattice effect? Well, this is how they contacted me and say, Marcelo, let's measure the lattice because the referee doesn't want to accept the paper. So we measured this. We found that the anomaly is very small. I mean, this is included in the paper in the supplementary information. But now we have our own paper with the lattice distortion. This is a confirmation. This is a way to show you that these are indeed quantum oscillations. This is the same measurement done now at 18 degrees of the A-axis. This is to study the oscillations in the A-axis, so that's why the this transition shows differently. But again, it shows you, very clearly where the transition is. You see oscillations at very low temperatures. I believe this is like 1.3 Kelvin, and all the way to 7 Kelvin, and they disappear as you go up. You take the oscillations over here, and then you can do the Fourier transform. And these frequencies, 450 Tesla, so on and so forth, appear. We don't see the very high frequency oscillations. This is typical of the lattice response. The high frequency oscillations are much more difficult to see. But then we also take the Fourier transform for the different temperatures, and we calculate this Lifshitz-Kosevic formula with all the amplitude of the oscillations in the Fourier transform, and obtain an effective mass of 1.35 bar electrons, which is very, very consistent with the spectra that was measured a number of years ago from magnetic properties by Cornelius and collaborators. One thing that's interesting here is that the peaks are at the correct frequencies. Let's see, there's 400 here, there's a 400 here, this one here, etc. But the intensities are different, and that means that different is the wave functions that couple strongly or less strongly with the atomic positions, right, with the localized moments. So magnetostriction and magnetization give you slightly different information on which ones are the orbitals that participate in the lattice bonding. So this is information that you can use potentially to simulate or to calculate the properties of this material. So I have like 7 minutes left. I think I'm getting to the end of it. And I think we have, like plenty of time to put you on the stage right now and see how many questions you can come up with. So let me repeat now my conclusions. I work for the National Magnetic Field Laboratory. This lab is open to all qualified users worldwide. You submit a proposal, you get magnet time, you run the experiment. No matter what, it's for free. First-time users get support for travel expenses. So even if you don't have any money in your grant right now, you can contact us and we will find a way to do the experiment. Piezomagnetism in uranium dioxide shows linear magnetic friction that is linked to a broken time reversal symmetry. This is a non-collinear 3K antiferromagnetic state discovered at 70. So this material still shows tricks that were not known before. The switch effect is likely due to antiferromagnetic domains. The model Hamiltonian reproduces the main features, and no electric quadrupole interaction with the U spin is required for this explanation. In the nematic electronic state of cerium, rhodium, indium 5, the antiferromagnetic state holds a puzzling state for H larger than 28 Teslas. The transport anisotropy points to a nematic state. The dilatometry points to XY type nematic state. We don't know yet if the nematic state is related to the presence of the quantum critical point or the superconductivity. There are plenty of examples for both in the literature. Thank you very much.